Hello, welcome to the course Electronic System Design. Last few lectures we are discussing about the logic gates, and we saw we have two types of gate, one is combinational circuits and one is the sequential circuits, and both of them are used as per the need. For example, the combinational gates are just the logic implementation we are doing on some set of inputs. We are performing some function on this set of inputs producing the output. However, if we want some synchronization at some place, then we are using sequential circuits, which is synchronized using a clock signal, which is a universal signal for a chip. Locally we generate a clock signal for a chip, it is unique, and whole of the chip is all the timing for the chip is determined using this single clock. So these are the logic gates or logic circuits which we use to implement functions, and a complete electronic system is nothing but the combination of these functions itself. So for example, we have two inputs, we have implement a function using two inputs, then we have two more inputs, we implement certain other function, then combinedly we have two outputs, we again perform certain other function on that, and this is how we build up a complete system by implementing multiple functions on these input parameters. So now we have gates which are available to us, combinational and sequential. Today's lecture we will see that there are certain techniques to implement these functions. These are not simply NAND and NOR, but we can implement even complex expressions using these techniques on the set of inputs, and we will see that there is something called Boolean algebra. We will study Boolean algebra, that how we can implement a complex logic function using these simple NAND, NOR and various other gates. So let us study the Boolean algebra today. So we have some basic logic operations here which are nothing but AND operator, OR operator, NOT complement, which is a complement signal. So these are nothing but some mathematical operators. For example, AND is like a multiplication, OR is plus, NOT is kind of a negation of a certain logic level, and they exist and they follow a order of precedence. For example, NOT, then AND, then OR. This is very similar to a mathematical precedence rule, which is, for example, BODMAS in mathematics we follow. So very similar to this kind of rules, we have order of precedence in Boolean algebra itself, and this can be modified using parenthesis. So if we write something in parenthesis, this comes first, so whatever is inside that will be analyzed, that can be computed first, then the rest of the operation will be performed. So these are some basic logic operations. When we have these basic logic operations, what does it mean? For example, we have AND gate, which is nothing but a combination of PMOS and NMOS. Then how do we specify the output versus input for this AND gate? So that is given by this table, which is called truth table of logic operations. This AND gate, for example, this has two inputs x and y, and the output is x dot y, which is AND of these two variables. So these variables are logical, it means they are having two values only, either 0 or 1. So for two variables there are 2 to the power n unique combinations, it means 2 to the power n for these two, it comes out 4 because n is 2, the number of inputs. So there are 4 unique combination, which is 0 0, 0 1, 1 0, 1 1, and the AND operation, if we perform on these two variables x dot y, for input 0 0 the output is 0, input 0 1 output is still 0, input 1 0 output is again 0, and for the input 1 1 the output is 1. So, this is the truth table of a AND gate. Similarly, we have for OR gate, which is x plus y now. So, 0 0 is 0 and rest combination 0 1 is also 1, 1 0 is also 1 and 1 1 is also 1. This is the truth table of OR gate. And then we have a NOT gate, which is nothing but an inverter. We can see this simply as an inverter. When the x is 0, the x dash, which is the output, is 1, and when x is 1 the output is 0. So, this is nothing but an inverter, and this is the logic or the truth table of logic operations on these basic gates. These are the symbols of these logic gates. This is 2 input AND gate, and we express it using this symbol. We have 2 inputs and 1 output. This is 2 input OR gate, where you have this kind of a symbol for OR gate, and for an inverter we have already seen this is the symbol for inverter, which is x is the input and x dash is the output. Now, there are other logic operations as well. For example, we have just talked about AND, OR and NOT. So, there are many other operations or many other gates available for us for designing. The very first one is the NAND gate, which we saw few lectures back. We had two PMOSes on parallel on the top and 2 NMOSes in series on the bottom. This is A, B, this is A, B, this is the output. So, this is something called a NAND gate, and the function which it performs on the input is A dot B tick, or we can write A dot B is the AND and the negation of this is NAND. So, this we can specify sometimes by this tick, or sometime we can write as a bar on top. So, A dot B bar is the NAND gate. Similarly, we have NOR gate where we have A plus B, which is OR, and the negation of this is NOR. So, this is the function. Similarly, XOR gate is the gate where the output is 1 if and only if either input is 1, but not both. So, for example, you have 0 0, 0 1, 1 0, 1 1, these are x and y values. So, the output is 1 if and only if either input is 1. So, either input is 1, this is 1, it means this is 1, this is 1, but not both. So, this 1 1, this is not 1, this is 0, and here it is 0. So, this is one of the gate which is very widely used in logic design, because if we see a very good property here, this gate can act as a comparator. For example, we want to detect whether two signals are same or not, then this gate is very useful. For example, when both the signals are 0 or both of the signals are 1, then the output is 0. If any of the signal is, or out of these two, both signals are different, whether it is 0 1 or 1 0, that time the output is 1. So, we can say if both are different, then output is 1, and if both of the signals are same, then output is 0. So, this gate is very widely used as a comparator or a digital comparator in our logic design. Another logic gate is XNOR gate, which is nothing but the output is 1 if and only if both inputs are 1 or both inputs are 0. So, this is exactly kind of dual of the previous one. We have x and y, 0 0 0 1 1 0 1 1, these are the 4 states, and the output is 1 if and only if both inputs are 1 or both inputs are 0, and this is both inputs are 0, then also it is 1, otherwise this is 0. So, this gate also can be used as a comparator. It will give you output 1 if signals are same, and it will give you output 0 if both of the signals are different. So, these are some of the logic operations which we perform using these gates, and these are, let us say, some other additional logic operations. For example, this is a NAND gate and this is a NOR gate. Here we see this is a XOR gate where the symbol is this additional line here before this OR gate. So, this is an OR gate, and if we place another line something like this, so this is a XOR gate. Similarly, this is a NOR gate, and we put additional this line, this is XNOR gate. Now, these truth tables, this truth table what we have just seen, we have x and y value, and one side we have output, and we write all the possible combinations of the input pattern. For example, we have 2 bits, then 0 0 0 1 1 0 1 1, and based on that we have certain output. So, this is called the truth table of a gate. This truth table is used to describe the functional behavior of a Boolean expression or whatever the logic circuit is doing. So, as we discussed earlier, we have, for example, a NAND gate. It has 2 PMOS on top in series and 2 NMOS, 2 PMOS in parallel on top and 2 NMOS in series at the bottom. Then we have, this is the NAND gate operation, and we have when 1 1 is there, then it is 1, otherwise 1 1 is there, then it is 0, otherwise it is all 1. So, in this case, for example, this NAND gate has its own truth table which is used to describe the behavior of this circuit. So, we make these circuits using PMOS and NMOS, and then we analyze what is the truth table which we have implemented using this gate. Each row in the truth table, for example, these are the rows, each row in the truth table represents a unique combination of the input variable. So, for 2 variables we have 2 to the power. So, if we have n variables in our gate, then we have 2 to the power n unique combinations. So, here we have 2 variables, it means 2 to the power 2, which is 4 variables, 4 lines we have. These are the 4 unique combinations in our truth table. The output of the logic function is defined for each row. So, for each row we have a defined output in the output column. Each row is assigned a numerical value with the rows listed in the ascending order. So, we can list down the numbers as well, 1, 2, 3, 4 and so on. The order of the input variables defined in the logic function is important. So, this is the order in which the input variables are defined, that is also important. For a truth table, when let us say we are talking about 3 input truth table, it means it has 2 to the power 3, which is equal to 8 unique combinations. this we can see as a function that we are implementing a function, and that function is actually in the form of a Boolean expression. So, whatever is the function we are implementing, for example a dot b plus c, this can be one of the possible function or the truth table of the gate. So, this is called a Boolean expression. So, for example, the same for the 4 input truth table, we have now 2 to the power 4, which is 16 unique combinations, and any function, for example we are implementing a plus b into c plus d, can be any expression. So, this is called the Boolean expression. So, let us talk about a little bit about what is a Boolean expression. So, Boolean expressions are composed of two things. One is the literals and the second is the logical operations. So, what is a literal? Literal is a variable and their complements. For example, a, b, b bar, etc. All these inputs which are coming to the gate, these are generally the literals, we call them literals, and the logical operations we are performing on them, they are logical expressions. For example, we are doing a plus b. So, this is the logical operation we are doing on these literals. So, here we have literals a and b, and the logical operation we are doing is plus. It can be a multiply as well. So, here we are doing a multiplication or the dot of a and b. So, this is the example of literals and logical operation. We have this function f, which is nothing but a 3 input expression. We have literals here a, b and c, and we are performing certain functions on them, which is, for example, this plus sign we are doing on this dot we are doing on this. So, these are the literals or the logical expressions on these literals. Similarly, we have another function here, we have a plus b plus c dash. So, here we have these literals a, b and c dash, and the logical operations, this plus and this plus, all these are logical expressions. So, based on this combination of literals and logical operations, we can perform different type of functions. So, for example, all these 3 functions, these are only with for 3 input variables, for example a, b and c. Based on these different combinations, we are implementing different functions. So, the Boolean expressions are realized using a network or the combination of logic gates. So, for example, in the previous slide itself we have seen here, if we talk about this thing, then we have certain terms in the Boolean expression. For example, these are the 4 terms which are added by this plus sign. So, plus sign is nothing but the OR, and these dots are nothing but the AND gate. So, for example, for first term, if we want to write, we have A and then B bar. B bar is nothing but a signal B with inverted input. This B bar comes here, and then this C, and then we are multiplying A, B bar and C. So, A, B bar and C, they are passing through a AND gate. This is one output, let us say output 1. Similarly, we can implement another digital gate for A dash B C dash. So, we have now A dash is inverted, B is directly going there, and C is again inverted, and then we have this output 2, which is 2. Similarly, output 3 will come for this, and output 4 will come for this, and then all these 1, 2, 3 and 4 are further added using this plus sign. It means one OR gate will be there, which is adding all of these 4 signals, and this is my F. So, this is how we look at the Boolean expressions, that these are the terms, and for each term we implement a Boolean logic circuit and then add them together to make a complete function which is implementing on these 3 inputs A, B and C. So, here these Boolean expressions are realized using a network or the combination of logic gates, very similar to what we just saw in last slide. This is one of the implementation of certain Boolean function. Each logic gate implements one of the logic operation in the Boolean expression. For example, we have A, B, C bar. So, there is one logic gate which is implementing this expression in the Boolean expression, and each input to a logic gate represents one of the literals in the Boolean expression. This is a sample logic circuit which is implementing a function which is a function of 2 variables A and B. So, we have 2 variables A and B, and it is implementing certain logic which we can easily decode even from this circuit itself. This A and B both are going to an AND gate. It means the output here is A dot B. Here this is A is passing through an inverter, so this becomes A bar, and this NAND, which is, let us say this is AND 1, this is AND gate 2, this is A bar into B. So, this is A bar into B, this AND gate which is 3. Now, this signal is B bar because B is passed through inverter. So, now this is A bar, this is B bar. So, this signal is A bar into B bar, and all these 3 signals are further added using this OR gate. So, you can write easily the function here is A dot B plus A bar into B plus A bar into B bar. So, we can even backtrace the logic function from the circuit itself, or we can implement the circuit using this Boolean expression. Both of the things are possible. Now, the Boolean expressions are evaluated by substituting a 0 or 1 for each literal. So, how do we evaluate a Boolean expression, what we just saw in the last slide? Let us say we have a function which is nothing but A dot B plus A B bar plus A bar B bar. So, how do we evaluate whether the Boolean expression is correct or not? So, we have here 2 literals A and B. We take all the possible combinations of A and B and compare it with the output. So, A and B, there are 2 inputs, so there will be 4 possible combinations 0 0 0 1 1 0 1 1. So, substituting a 0 or 1 for each literal, we can evaluate and calculate the logic value of the expression. So, this expression we can calculate the value of this for this possible combination. Let us say for 0 0 we want to calculate value of this, that will come here. For 0 1, A is 0, B is 1, then that value will come here, 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 and this is how we calculate the Boolean expression. and the truth table specifies the value of the Boolean expression for every combination. So, when we do this exercise, this is nothing but the truth table we end up with. This becomes the truth table of that gate or the Boolean expression what we are implementing. And as we discussed, for an n variable Boolean expression, in the truth table we have 2 to the power n rows, one for each combination. So, for 4 inputs we have 2 to the power 4, which is 16 rows. For 5 inputs we have 32 rows. For 6 inputs we have 64 rows, and so on. If we see very carefully, with just one increase of the input from 5 pins to the 6 pins, just one increase of the input, the complexity or the number of rows actually doubling from 32 to 64. It may be okay, but even for if we go for 7 input gate, then we have the complexity in the logic in the truth table is 128 rows, which will be very difficult to implement because the complexity is going exponentially in 2 to the power n. So, it is desirable to not to have a very large number of inputs to a single gate. So, because the complexity increases very drastically. Now, let us see one example where we evaluate the following Boolean expression for all possible combinations of inputs using a truth table. So, for example, we have this Boolean expression and we have these 3 inputs A, B and C. So, we will have 8 possible combinations A, B, C, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then we have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are all the possible 8 combinations, and based on that, if we implement this, put this 0, 0, 0 here and calculate what is the value here, we can find out the value of this truth table. This you can do it at home. Now, we have seen the Boolean expressions, which is nothing but some algebraic expression for the input pattern. Now, if we have 2 Boolean expressions, then how can we know that both are equal or both are not? So, the 2 Boolean expressions are equivalent, or we can say the same, if they have the same value of each combination of the variables. Or in other words, if we make a truth table, so for example, this is input and this is output, this is truth table for 1, and for truth table of second gate of second expression is exactly same as the truth table of first, then we can say both of the Boolean expressions are equivalent. So, for example, this function 1, which is a plus b bar, and f2 is a bar dot b bar. So, we can write in this way, function 1 is a plus b bar and function 2 is a dot b whole bar. If we want to check whether these two functions are same or not, then we simply put values of a and b, which are 4 unique combinations, and if the output f1 is exactly same as output of f2, then both of these expressions are equivalent. And how do we prove that? That can be proved first as truth table, as we just saw. We put values of a and b, all unique combinations, and we calculate output. If it comes out same, then both are same. The second way of proving that they are identical is Boolean algebra. Boolean algebra is nothing but simplification of these Boolean expressions. So, we have seen these, just like an equation, we have these Boolean expressions and we can perform certain amount of simplification so that the expression actually shrinks to a smaller value, and if both expressions comes to be the same at some point, then we can say the both of the Boolean expressions are equivalent. But for that we need to know what is a Boolean algebra. So, for example, using a truth table we can prove that the following two expressions are equivalent, a plus b bar and a bar into b bar. These comes out to be the same. So, this is one method. The another method is the Boolean algebra. So, what is the Boolean algebra? Boolean algebra is actually, in the George Boole developed an algebraic description for processes involving logical thoughts and reasoning. So, he developed a set of algebraic rules for logical thoughts and reasoning. This became known as the Boolean algebra later on. However, Shannon later demonstrated that Boolean algebra could be used to describe switching circuits. So, the Boolean algebra is a general term, however, you can implement the same logic or the same rules what George Boole has developed. The same rules can be applied to switching circuits such as our logic gates, which are NAND NOR gates. So, you can apply these Boolean algebra rules. These switching circuits are circuits built from the devices that switch between two states, for example 0 and 1. And switching algebra is a special case of Boolean algebra in which all variable takes on just two distinct values. So, in Boolean algebra we assume that the input and output takes only two values, one is the low state 0 and one is the high state which is 1, and this is perfectly suitable for our switching devices, for example our NMOS, PMOS and other logic gates, NAND NOR gates, where the logic states are always 0 as a low or high as a 1. So, we can apply directly this Boolean algebra, and this Boolean algebra is a powerful tool for analyzing and designing logic circuits. We perform this Boolean algebra all the time in designing these digital circuits. So, there are basic laws and theorems in the Boolean algebra. There are so many theorems which are available. For example, just like our normal algebra, we have so many rules. For commutative law, for example, a plus b is equal to b plus a in Boolean algebra as well, which is in the summation form, and in the product form it is a dot b is same as b dot a. So, this is commutative rule. Similarly, we have associative rule, which is a plus and then b plus c is nothing but a plus b in parenthesis, and then we have plus c. In the multiplication form, we have a dot b dot c equal to a dot b and then whole dot c. So, this is associative rule, and we have so many rules here, you can go through it. Boolean algebra generally takes much time to analyze and study well. So, in one lecture we cannot go very much in depth, but these are some of the rules and theorems which you should know. So, there are so many laws and theorems. We can go for one or two rules in detail. For example, idempotence, this is one of the rule which says that a plus a is equal to a. So, here the thing is, In normal algebra, what we just follow, we always follow that 1 plus 1 is equal to 2. In normal algebra, it comes like this, but in Boolean algebra, the 1 plus 1 is 1. So, this is different than our normal algebra, that for the Boolean logic or the Boolean algebra, the 1 plus 1 is 1. Though it looks different, but if we think about the electrical circuits, that we are implementing this algebra to electrical circuit, then it makes sense. For example, we have a single node and we want to measure how much is the output, and there are two gates which are writing output on this. At this node. So, gate number 1 is producing 1 volt and gate number 2 is also producing 1 volt. So, here the output, which is kind of wired OR output, this output is not 2 volt, it is 1 volt, still 1 volt, because 1 volt will come from here and the 1 volt will come from here. So, the output resultant voltage is only 1 volt. It is not actually 2 volt, voltage will not add up, it is just the volt, this node is driven by 2 voltage sources of 1 volt. So, if we think about our electrical logic networks, then this Boolean algebra makes sense. We have A plus A is equal to A only, it is not 2A. So, the same logic we can actually extend to multiple to the terms which has multiple literals. For example, this function f, we have ABC plus ABC bar plus ABC. So, here we can see this ABC term is actually coming 2 times here. So, we can extend the same rule, A plus A is equal to also A. So, we can get rid of this one term, we write it only once. So, actually this function which can be reduced to ABC plus ABC dash. So, this is one rule. Similarly, A dot A is also 1, A dot A is also A. So, for example, we multiply 1 by 1, this is also 1. So, the same rule we can extend to multiple literal terms. We have this function g, where we have a dash plus b plus c dash, a plus b dash plus c, and then a plus b dash plus c. Then we see that this term and this term both are same. So, we need not to write it 2 times, we just get rid of this one term. We write a dash plus b plus c dash and plus a plus b dash plus c. Now, we have complement rule. What complement rule says, a plus a dash or a plus a bar is 1. What it says, if I have an input of, for example, 0, then the inverted of this will be 1, and if we add both of them 0 and 1, the output will be 1. For example, in other case, if the input is 1 and we add it with the inverted case which is 0, then also the output will be 1. So, any literal or any group of literal, if the resultant is A, it is added to its own negation, then the output is 1. So, this function a b c dash d plus a b c d, if we take common a b d, a b and d, then c dash plus c comes inside this parenthesis, and c with its addition with its own negation is actually 1. So, the resultant is a b d. So, this is how we actually simplify the Boolean expressions. We apply these rules on the expression. For example, this is the expression which is a bit longer expression. Now we have applied this complement rule on this expression, and the final expression is way simpler than it was earlier. This expression or the optimization of expression is very important, because if we see carefully here we needed 4 input AND gate here, A, B, C dash D for this block, and 4 input AND for this. Let us say this is term 1, this is term 2, for this is term 1, term 2, and then we have to add. So we put a OR gate here, 2 input OR gate, which is for this combination. So this is function f. So here we see the complexity. We have 4 inputs here, and we have 4 input gate here, and then 2 input gate. However, if we simplify this logic using this complement rule, then we have only a term ABD, which is nothing but a single term, a 3 input AND gate. A, B, D, and this is F, which is these and these two functions are exactly same. However, in this we have 4 input gates, and that 2 in number. Here we have only 3 input gates, only 1 is needed. So we can see that the hardware complexity is very much optimized from going from the top to the bottom. We have saved so much of area and gates by implementing these Boolean expressions. So this is one of the rule. Then we have the second rule, which is A dot A dash, which is also equal to 0. So this we can implement on this logic expression, and we can reduce this to a very manageable small Boolean expression. There are other laws as well. For example, distributed law, it means A dot B plus C. It can be written as, we remove the bracket, then A dot B plus A dot C. Similarly, if A plus B into C, we can write A plus B into A plus C, and we can again implement on certain Boolean expressions. This is absorption rule. This is A plus A into B is nothing but A, which this we can prove simply by taking the A as a common. So if we take the common A from this left hand side, this becomes 1 plus B. So anything 1 plus B is always 1, because even if B is 0, this 1 plus B is 1. If B is 1, then 1 plus 1 is also 1. So this term is always 1. So we end up with A only, A dot 1 or A. Similarly, we have this side A dot A plus B, which is equal to A, and we can apply this rule to the logical expressions. This is simplification rules. A plus A dash B is nothing but A plus B, and A dot A dash plus B is equal to A dot B. Logic adjacency, which is nothing but the combining of these terms, A dot B plus A dot B dash is nothing but A, which this we can write simply by taking A as common. So if we take A as common here, then inside becomes B plus B dash, and this we have just seen, B, any literal with its complement is always 1. So this is A into 1 or A. Similarly, we have this rule A plus B into A plus B dash, this is also equal to A. So we can take some example on Boolean algebra. So using Boolean algebra, simplify the following Boolean expressions. So this is the Boolean expression given, and you need to apply now Boolean rules or whatever rules we have just seen on these literals. For example, taking some literal common, a common here, b common here, and then simplify this expression to a optimum value. Then we come to a very important law of Boolean algebra, which is De Morgan's theorem. So, the De Morgan theorem can be stated as follows: the complement of the product and is the sum of the complements. What it says, let us say we have two literals and then we have these literals are and there is overall negation, overall bar on top, then this is equivalent to, we break this bar on individual literal and change the sign in between. So, this x dot y becomes x plus y. So, dot becomes plus, the multiplication becomes plus, and this bar on top x dot y, this whole bar, this bar breaks individually on the individual literal. So, the De Morgan's theorem says x dot y bar is equal to x bar plus y bar. So, this is one rule, and similarly if we have x plus y bar, x plus y, and there is a whole bar on top, then this can be written again with the same law. We change the sign in between, this sign, we change the sign and we break the bar on individual literal. So, we change the sign to x dot y now and break the bar on individual. So, now this becomes x dot and y dot. So, this is the De Morgan's law, which is very much used in simplifying the logical expressions, and this can be easily generalized to n variables. So, these only two, there need not to be only two variable, it can be, for example, x y dot z, and then there is a whole bar, then we can also write it like x y plus z, and then on the individual there is a bar. So, this rule can be easily generalized to n variables or more than two variables, and it can be proven using a truth table. If you want to prove this rule, that this rule is correct, you can make a truth table for two input expression and you can calculate these values separately and it will come out to be equal. For example, this is De Morgan's law. We have x dot y bar and we are saying that this is equal to x dot x plus y and then individual bars. So, this we can prove using truth table. So, we have in truth table we have two variables x and y, and these are all possible combinations 0 0 0 1 1 0 1 1. Now, we calculate first the left hand side, which is x dot y and then whole bar. So, we first calculate x dot y, which comes out 0 0 0 1, and then bar of x dot y, this is x dot y bar, which is inverted of x dot y. So, this is 1 1 1 0. So, this is our left hand side. On the right hand side, what we have, x bar and y bar. So, first we calculate x bar and y bar. X is here, so x bar is 1 1 0 0, y bar is 1 0 1 0, and then we calculate x bar plus y bar, which comes out to be 1 1 1 0. So, this is our right hand side, and now we see this LHS is equal to RHS. If both of the sides logical expression is same, it means this rule is correct, which is De Morgan's law. So, we can prove it using the truth table, and this is the only the pictorial view of De Morgan's law, where we have, this is a NAND gate, which is implementing x1 dot x2 bar. So, this is x1 and x2 and this is x1 x2 bar. This we can write using this OR gate and then inverter. This is NAND. So, this comes out to be a gate where x1 bar plus x2 bar, this is adding up both of these negated literals. Similarly, for this x1 plus x2 whole bar, this you can write using this NOR gate. x1 and x2 are producing x1 plus x2 whole bar. This you can implement using x1 bar individually and x2 bar and then AND of these two literals. So, this is the De Morgan's law. Now, the importance of Boolean algebra. So, Boolean algebra is actually very much used to simplify Boolean expressions through application of the laws and theorems discussed. So, we have so many laws and theorems these we apply on the Boolean algebra, on the Boolean expressions and reduce them to a optimized form. Simpler expressions, actually whenever we optimize the expression, we make it simplified. This lead to simpler circuit realization as we just discussed. Earlier we had two 4 input gates and then one OR gate. Instead, if we simplify, we just need a simple 3 input AND gate, which is implementing the exactly same function. So, simpler expressions lead to simpler circuit realization, which generally reduce cost. The cost is actually how many circuits we need to implement a single function. If it reduces, the cost reduces. The area also requirement also reduces because you need less area to implement less logic gates, and power consumption also reduces because you need lesser circuits. The objective of the digital designers actually is to design and realize optimum digital circuits. So, when a digital designer actually implements this logic, his whole intention or the objective is to reach to a optimum digital circuit. This Boolean expression actually reduces the cost associated with realizing the expression using logic gate. It reduces the area as we just discussed and reduces the power consumption. Though in general there is no way to determine whether a Boolean expression has it simplified to a minimum number of terms or minimum number of literals. So, there is no unique combination or no unique solution if you optimize these Boolean expressions. So, it depends on which law you are applying on that Boolean expression. Based on that, you can have a unique solution compared to the other one. So, there is no a unique solution if you are optimizing 2 times, 3 times. It may possible that you end up with a different output compared to the previous one. So, there is no easy way to determine whether you have reached to an optimized number of terms or number of literals. So, today we have discussed that Boolean algebra is a tool by which we can implement the logic expressions, and these logical expressions or the Boolean expressions we call them, we apply certain rules and theorems to optimize them further. The more we optimize, the more we can shrink the logic function, the lesser hardware requirement we have to implement that system. So, if we reduce the number of logic gates in our circuit, we can save on the cost of fabrication, we can save on the area of fabrication. In the limited area we can put many functions, and we can improve on the power dissipation of the circuit, because if we have lesser gates then power dissipation will be lesser. So, this is some idea about the Boolean algebra. That is all for today. Thank you.